All right, so now let's do some attacks and defenses. Coming down here. Now, one thing about these attacks and defenses is that most of them use this security ML library, which unfortunately hasn't been updated in a couple of years. And if you use Python libraries, you'll be used to this. Everybody keeps changing everything. So after a while, your library needs old versions of dependencies, which you can't easily install anymore. So you can't use Google Colab to do these projects. So I made a special virtual machine that has an older version of Debian that you can run. And if you download and run this virtual machine, you'll then have Jupyter notebooks yourself running on a local machine, which has the older versions necessary for these projects to work. So you can launch a notebook here, and it works just like Google Colab, but it's actually running on a local virtual machine, which has the right versions for these attacks to work. And so you can create a data set here, and this is going to be just a synthetic data set with three different colored blobs, as you can see. The goal is to separate these into categories. And we can do this with support vector machines from before, where it just draws a line as a decision set between them. And so you can create and train the model, and you'll see it's 98.8% accurate. And you can visualize the decision boundaries, which appear like this. They're not straight lines in this graph, but in some mathematical sense, they're straight line in higher dimensional space. So it does a pretty good job of separating those three categories. And now we can talk about what an evasion attack would be. Once you've trained your model to do some job, an evasion attack is where you give it malicious input that fools it into miscategorizing it. So here, for example, they train something to recognize animal faces, and so this would be called a panda with 57% confidence. But when they add a tiny bit of random noise, carefully chosen, apparently random noise, now it's a gibbon with 99% confidence. So this is the fundamental issue. This categorization was not done the way a human would do it by noticing like an eye and a nose and stuff, and then putting those features together, which is how we believe humans do it, although I'm not a visual psychologist and there may be more complicated things there. But this little bit of noise that a human can't even see is enough to completely fool the machine learning model because it did something like decide this pixel here is really important and these three pixels over here are super important and the rest don't really matter. So when those pixels change a little bit, that totally changes its perception because it doesn't see what we see. And in the same spirit, there was a research project about a year ago. China has a bunch of AI robot taxis already running out there. So they took the visual system of those robot taxis and they carefully designed a bumper sticker looking thing with just a few dots on it. And if you put that on a car, the taxis can no longer see that car. It no longer recognizes it at all, and it'll plow right into it. And that's the kind of thing that comes from these evasion attacks. So we can perform an evasion attack here. And what this SecML library does is it calculates the most effective thing to do. So if you take a dot and move it, and you're only allowed to move a dot a certain distance, you're only allowed to move this one dot, you can figure out where would I put that dot to do the most damage to the model. So you figure out how sensitive the model is to each of these input parameters, input data, and find moving that data up here and leaving it red would do the most damage to the model. And then you can do security evaluation. And so determining how far you move it, the accuracy of the model falls from nearly 100% down to random chance, which is 33% when you completely foul it up. So you can calculate if the model is a public model and you know all the weights and all the structure of it, then you can carefully calculate the easiest way to poison it, or I should say, to evade it. Poisoning is changing the training data so your model learns bad habits. Evading is taking a model that's already been trained and presenting it with an input which tricks it into miscategorizing it. So, a few flags to find there. So we can try doing it on something easier to see, these letters that we're categorizing instead of just those synthetic dots. So we get one of these databases of labeled images, like here, and we're only going to do the fives and nines. So it's separating, it's determining whether they're fives or nines. We train a classifier, and the classifier is 100% effective on the test set. All right. But after the attack, it shrinks down to 12%. So the attack is very effective. And in this attack, we're going to move 25 of the images. We're going to poison 25 images to fool the model or evade with 25 of the images. And you can see them here. Here's the images. So this is the original 9, which was categorized as the 9. Here's the poisoned 9. Sorry, still getting the word wrong. This is the evasion image for 9, where this little bit of snow makes it misidentified as a 5. And this is the snow that turns a 5 into a 9. All these images are incorrectly classified now because of this little bit of snowy stuff added to them, exploiting the fact that the model does something very different than humans. So you can try smaller perturbations, you can try different perturbation types, and so on. But this shows you what it takes to evade a trained model. Now, I wondered what we could do for defense, and it took me a whole week to write this project because it came in a research paper that was very dense and hard to understand. But the trick is this. You have your whole model here with layers of processing that analyzes an image. And then you put 3 models on the side, which make some kind of summary of the shape of the image. And then you combine them into one number, which is some kind of measure of the shape of the image, and you find the outliers. The idea is you can spot that these images just look funny. They have this funny snow in them, and the others don't have that snow in them. So this is the machine learning way of doing that. So you prepare the entire model. First, you train a model to categorize these images of the unprotected model, and it does pretty well. It gets all these right. The right answer is 7. It predicts a 7. The right answer is 6. It predicts a 6. It's pretty good. Here's one it got wrong. Right answer is 5, but it predicted a 3. But you can see, I guess it might, you see the 3 is 712, the 5 is 730, so it's easily confused. I guess I got the right and predicted reversed there, but it doesn't matter. You can see it's doing pretty well, although it's not perfect. Now you can attack this model. And remember, this attack is a very smart attack. It has access to the entire trained model to calculate the most efficient way to make images evade classification. So here it is, adding this snow to the images. And you can check to see what happens. And the answer is, out of the 20 images that you added the evasion snow to, all 20 of them are now miscategorized. So the attack is 100% successful. Now, for a fair comparison, you now add the deep neural rejection to it. So you add stuff to the model that will measure the shape of the image and throw it away if it's an outlier. And now you can view the predictions and the rejections. And what happens is, here's the first 20 images, and some of them it rejected. Number 15 and 18, it rejected. And number 8, some of them look funny, but the rest it predicted correctly. And now you have access to the entire model, and now you calculate evasion using all the information about the model, including the information about the deep neural rejection. It formed the same evasion attack and poisoned these images with this extra junk. And now what happens is, when you evaluate the evasive images, most of them are detected as unacceptable and it refuses to make a prediction. The -1 means it decided not to categorize it from 0 through 9. It was able to detect that they were bad. So the only number of successful evasions is now 6, and before it was 20. So you can see that this defense is relatively effective. So you can set all that up and run it. You want to see it? That's a real attack and a real defense that stops the attack. So I'm going to stop this one.